The night sky lay in its usual silence, a vast cathedral of ancient light stretching over the observatory. Stars shimmered like distant memories, their glow softened by the slow breath of the atmosphere. Beyond them, galaxies drifted in cold procession, moving through a darkness so deep it seemed untouched by time itself. Nothing unusual stirred. Nothing suggested that the universe was about to reveal something impossible. Inside, the radio array's data stream. Faint pulse appeared, deliberate, impossibly precise. It slipped into the logs like a whisper carried across the cosmic ocean. So light and fragile it might have been dismissed as noise. Yet its pattern did not belong to cosmic background radiation, nor to any known pulsar, quasar, or deep space echo. It bore the unmistakable architecture of an encoded message. But the true fracture in reality lay not in the signal's structure, but in its tamped. The pulse had arrived hours before the observatory's own outgoing calibration signal, the very signal it matched perfectly. According to every atomic clock synchronized across Earth and deep space, the message had reached the antenna before it was ever transmitted. In the stillness of that cold night, a deeper question began to unfold. How does information travel from a future that has not yet occurred? What kind of universe allows effects to precede their causes? What hidden geometry of spacetime can bend so sharply that a message circles back on itself? As the signal faded into the noise, one realization lingered like a shadow across the stars. Time might not be a straight road after all, but a looping, trembling fabric capable of folding under forces humanity has barely begun to imagine. 5. Escalation mystery deepens. What makes the mystery more extreme? A second pre-arrival signal appears, this time containing data that hasn't yet been created, the future-originating signal references. An update to equipment that scientists have not yet installed. Timestamp gap widens. Hours gives days gives, potentially weeks. Theoretical crisis. Are they witnessing a naturally occurring space-time loop? Or did the universe momentarily tear open a shortcut through temporal geometry? Existential implications. Information can travel backward through cosmic structures. The universe might not be a timeline, but a dialogue. Reality could be interacting with itself across its own past and future. The realization settled slowly, like a cold mist creeping across a quiet valley. In the days that followed the first anomalous detection, the team at Chime attempted to ground themselves in the familiar language of science: logs, timestamps, synchronized timing chains, and error sheets. Yet each return to the data only deepened the fracture that had begun to form in their understanding of reality. What they witnessed was not merely unusual, it was impossible. The signal's metadata was the first undeniable crack in the universe's logic. Encoded within the pulse was a precise sequence, a calibration template the observatory routinely used to test its own instruments. This template was not random. It had a specific structure, a distinct set of modulation steps, and a recognizable compression pattern. The signal they received matched this template with eerie perfection. But the calibration pulse associated with it had not yet been transmitted. It was scheduled for hours later. The encoded structure could not exist. Before its own creation, every attempt to dismiss the anomaly drifted into the same stone wall. The clocks were not wrong. The system logs were not corrupted. The outgoing pulse had not been emitted prematurely. The team verified this through multiple layers of independent timekeeping. Optical atomic clocks, whose precision defied imagination, showed no drift. GPS satellites, orbiting the planet with synchronized timing corrections for relativity, displayed perfect alignment. Even deep space timing relays, signals echoing from distant probes such as Voyager, confirmed that Earth's clocks were stable. Time, as measured by every human instrument, pointed forward. But the signal pointed backward. The contradiction grew sharper the more they studied it. The timestamps did not merely suggest temporal misalignment. They insisted upon it. The signal had arrived with a temporal signature. It implied its origin lay in the future relative to the equipment that detected it. The anomaly was not inconsistent with the systems. The anomaly was inconsistent with reality. A quiet unease spread across the scientific community as data files, traveled to research centers across the world. Scientists accustomed to confronting the unknown now faced something that resisted even the language of uncertainty. For decades, physics had expanded into strange territories: quantum entanglement, gravitational waves, dark energy, and the bizarre geometry of black holes. Yet even in the strangest discoveries, the arrow of time remained intact. It was the one constant that anchored the universe's unfolding story. But this signal had not waited for time to grant permission. It had crossed the boundary uninvited. The concept of causality became the central point of fracture. In physics, causality was more than a philosophical idea. It was a structural pillar woven through every equation, every experiment, every observation. Effects followed causes. Signals followed transmissions. Information moved forward through space-time like a river flowing downhill. This was not merely an assumption. It was a condition of the universe's coherence. Yet, the signal arrived while its own source remained in the future. What followed inside the observatory resembled the slow unraveling of an old tapestry. Threads of certainty loosened. Ideas once taken as absolute began to tremble. The scientists, though trained to avoid emotional entanglement with their work, could not ignore the weight of what confronted them. Even the calmest voices carried a subtle tension, as if aware that they stood on an edge humanity was not meant to cross. The core contradiction lay in the foundations of relativity. Einstein's equations permitted space-time to bend, twist, stretch, and ripple. Gravity slowed time. Speed compressed it. Black holes distorted it so severely that seconds stretched into hours. But through every distortion, the forward motion of time preserved its direction. Even in the curved geometry around black holes, causality remained intact, except in one peculiar scenario: the existence of closed timelike curves. These curves, predicted within specific solutions of general relativity, were loops in space-time where an object or a signal could, in theory, return to its own past. They were associated with Kerr black holes, rotating giants whose spinning cores twisted space-time like a cosmic whirlpool. Within such regions, mathematical solutions hinted at paths where time folded back on itself. For most physicists, these scenarios were mathematical curiosities, not physical realities. The conditions required were extreme, delicate, and likely unstable. No evidence had ever shown that the universe allowed such structures to exist in nature. But the signal, with its reverse temporal signature, behaved as though it had traveled along exactly such a curve. One question echoed through the observatory halls like a silent, haunting refrain: if a signal could defy time's direction, what else might be possible? The first wave of shock arose from the metadata, but the second wave came from the precision of the timestamp alignment. If even one of the atomic clocks had drifted, or if one GPS relay had malfunctioned, the anomaly could be dismissed as an artifact. But everything aligned with uncanny coherence. The GPS network itself, dependent on corrections for relativistic time dilation, showed no instability. Deep space timing signals, which traveled millions of kilometers, arrived exactly as expected. Earth's most precise clocks, based on oscillations of strontium atoms, agreed down to the nanosecond. This meant the time stomp was not an accident of instrumentation. It was a statement written into the fabric of the signal's journey. The contradiction moved from improbable to inescapable. If information could arrive before transmission, then information had traveled faster than light, violating Einstein's speed limit. But faster than light travel was only the surface issue. The deeper violation lay in the sequence of events. The universe, as described by physics, depended on a stable temporal order. Processes unfolded in one direction. Entropy increased. Stars formed, lived, and died. Galaxies grew and collided. Time marched forward. The anomaly implied that time might not be marching at all. It might be spiraling, folding, or branching in ways that perception could not grasp. When the CHIME team sent their findings to theoretical physicists, the responses varied from cautious skepticism to genuine alarm. Some suggested exotic interpretations, quantum retrocausality, where entangled particles could produce correlations that seem backward in time. Others proposed the involvement of tachyon-like particles, hypothetical faster-than-light entities that, if they existed, would naturally propagate information into the past. But most believed that even these exotic possibilities could not produce a macroscopic signal with perfect coherence and a clear, structured message. The anomaly was too clean, too intentional, too synchronized with human systems to be explained by spontaneous quantum effects. The shock deepened once deeper analysis revealed subtle distortions in the waveform. These distortions resembled the gravitational shearing expected if the signal had grazed a region of intense curvature, perhaps the outskirts of a rotating black hole. The dispersion was faint, barely detectable, but real. Yet the signal's clarity contradicted the turbulence expected from such an extreme environment. It was as if the signal had passed through a cosmic storm without being touched. More troubling still was the signature's lack of decoherence. Signals traveling through space usually degrade. Plasma clouds scatter them. Magnetic fields twist them. Cosmic dust absorbs them. But this anomaly exhibited extraordinary stability. It carried the fidelity of a signal transmitted from within Earth's atmosphere, yet its dispersion hinted at a journey far beyond. How could a message travel through the universe and emerge cleaner than a terrestrial broadcast? The paradox of its journey and the impossibility of its timing created a storm of intellectual tension. Conferences erupted with discussions. Papers circulated privately, their authors hesitant to submit them publicly. Nobody wanted to be the first to claim that time had bent. Nobody wanted to face ridicule. Yet nobody could explain the anomaly away. As the investigation deepened, sense of scientific shock transitioned from disbelief to existential concern. If the signal was real, then the universe had revealed a property hidden beneath the familiar surface of time. Perhaps time was not a river flowing in one direction, but a surface capable of being warped into loops. Or perhaps time, like space, possessed a geometry that could be folded, allowing two distant points in the timeline to touch. The implications were profound. If information could travel backward, then the causality protecting the integrity of the universe could be disrupted. A message from the future could alter the present. A decision made today could be influenced by a signal emitted tomorrow. Reality could become self-referential, recursive, or even unstable. This was the root of the scientists' quiet panic. Einstein's assumption that causality was inviolable formed the foundation of modern physics. Without causality, predictions collapsed. Experiments lost meaning. The future could influence the past, creating paradoxes where events contradicted themselves. A universe with broken causality was not merely unfamiliar. It was incomprehensible. Yet here lay evidence that causality might not be. Absolute physicists recalled the peculiarities of closed timelike curves, theoretical constructs in which time looped around in on itself. These curves appeared only in specific, extreme conditions, near occur black holes in a region, or within speculative wormhole geometries requiring negative energy. Most scientists assumed nature would forbid such paths through quantum instability or other protective mechanisms. It was widely believed that the universe defended itself against paradoxes, but the anomaly suggested that the universe might not defend itself as strongly as once thought. A signal had slipped through. A message had returned. A contradiction had formed in the fabric of time. In the quiet aftermath, the scientific world faced a problem more profound than any in living memory. The anomaly was not a distant cosmological curiosity. It was local. It involved human transmission patterns. It involved technology created on Earth. It involved the future of the very people studying it. The signal pointed back at them, like an echo from a path they had not yet taken. The shock, once intellectual, became personal. For the first time, the scientists sensed that they were not merely observing the universe. They were entangled with it. The world of physics had confronted many mysteries: dark matter, dark energy, the quantum vacuum, the inflationary birth of the cosmos, but always from the safe distance of observation. This mystery, however, reached into the flow of time itself and folded the observers into the phenomenon. It forced them to consider a universe where the future was not separate from the present, where information moved freely across the boundary they believed immutable. The anomaly did not simply challenge physics, it challenged the understanding of existence. Into this quiet, trembling realization came the final acceptance. What they had witnessed was not a glitch, not interference, not a misalignment of clocks. It was a rupture in the order of time. Small, precise, undeniable. The universe had behaved in a way it was not supposed to behave, and humanity, for the first time, stood before a contradiction so deep that even the laws of nature seemed momentarily unsure of themselves. The shockwave of the anomaly did not confine itself to a single observatory. Within hours, encrypted messages traveled quietly between institutions, reaching radio telescopes, data centers, gravitational wave facilities, and deep space communication hubs. What began as a local disturbance soon drew the attention of laboratories across continents, each one tasked with confronting a problem that had no precedent in the history of science. The world of physics had faced mysteries before, but this one demanded something deeper, a global introspection into the structure of time itself. Scientists across Europe, Asia, North America, and Australia initiated a coordinated sweep through their archives. Tracing every timestamp detection from the past decade, they combed through terabytes of data collected by cosmic background monitors, pulsar timing arrays, and neutrino observatories. Their task was monumental, to search for anomalies so subtle that earlier teams may have overlooked them, buried in noise or dismissed as timing drifts. In laboratories lit by the glow of monitors, researchers scrolled through cascading streams of numbers. Searching for echoes of something that should not exist, the global effort revealed patterns that, at first glance, appeared insignificant: faint pulses, partial sequences, fragments of modulated energy that held no clear meaning. But as teams layered the data and tightened their filters, a picture began to emerge. Scattered across years of observations were brief, fragile anomalies, nothing as clear as chimes detection, but enough to raise suspicion. These faint signatures shared characteristics with the primary anomaly: temporal offsets, unusual coherence, and dispersive patterns that suggested a convoluted path through space. None of these earlier fragments were identical to the calibration pulse from chime, but they possessed a similar signature: structure where structure should not exist, coherence where noise should dominate, timing irregularities where timestamps should align. What had once seemed like random glitches now resembled a series of faint pre-echoes, incomplete, fragmented but unmistakably part of a broader chain. As scientists stitched these fragments together, the anomaly widened in scope. The phenomenon was not isolated to a single moment. It had been whispering at the edges of detection for years, too subtle to notice until the perfect alignment produced the unmistakable signal. The next stage of the investigation moved from archives to analysis. Teams turned their attention to the nature of the signal itself, dissecting it through mathematical tools capable of probing the smallest anomalies. Spectral analysis became the primary method. Every frequency component of the signal was examined, separated, stretched, and reconstructed. Like botanists studying the rings of a tree to understand its history, physicists examined each harmonic to trace the journey of the mysterious pulse. A pattern emerged from the spectral signatures, delicate frequency shifts that suggested gravitational interference. These shifts were small but consistent, resembling the soft curvature induced when a wave passes near a massive object. In normal circumstances, such distortions would indicate the presence of a black hole or a dense neutron star. Yet the pattern did not match any known astrophysical environment. Instead, it hinted at something more extreme: a region where space-time itself was bent sharply enough to alter the temporal composition of the wave. To understand this distortion, scientists studied the modulation patterns encoded within the signal. The waveform's rise and fall carried hints of its origin, but also of its journey. It displayed a peculiar symmetry, a form of mirrored decay not typical of natural sources. As analysts magnified the waveform, they observed something extraordinary, a faint secondary signature buried beneath the primary modulation. Like an echo of the signal's own structure, this secondary layer was not a reflection from a spatial surface. It carried no indication of rerouting through interstellar matter. Instead, it appeared displaced in time. The echo seemed to precede the main signal, so the wave had interacted with a boundary not in space, but in the flow of time itself. The deeper the analysis went, the more uncanny the symmetry became. The signal behaved as though it had touched a temporal boundary, a region where the arrow of time was not strictly enforced, where information could scatter and return from a direction, orthogonal to normal chronology. Such pre-echoing had no conventional explanation. In standard physics, reflections require surfaces. Distortions require gravity. Decoherence requires turbulence. But a temporal reflection, a signal bending back along its own timeline, demanded something far stranger. A space-time surface capable of folding. Alongside these spectral revelations came the study of decay curves. As a wave travels through the cosmos, it loses coherence, scattering into the interstellar medium. Its amplitude decreases with distance. But the anomaly's decay curve was unlike any previously recorded. It dropped sharply at points where it should have remained stable, then plateaued where it should have faded. These irregularities were not random. They formed a repeating pattern, as though the signal had traversed alternating layers of extreme gravitational curvature and near-vacuum emptiness. The most compelling interpretation came from researchers specializing in gravitational lensing. To them, the decay curve resembled the imprint left when a wave passed near a region of variable space-time. Density, perhaps the turbulent boundary of a black hole's ergosphere, or the opening of a wormhole, if such entities were stable enough to exist. The distortions did not align perfectly with known models, but they contained the unmistakable flavor of extreme gravity. Yet the signal's coherence complicated these interpretations. A wave passing near a black hole should emerge distorted beyond recognition, its structure scrambled by tidal forces. Wormholes should warp the signal so drastically that reconstruction would be nearly impossible. But the anomaly emerged almost pristine, preserving the clarity of its original template with only faint distortions. Something had interacted with the wave, but not in a way consistent with known gravitational environments. These contradictions pushed scientists toward the quantum domain. Experts in quantum field theory examined fluctuations in the signal amplitude, searching for signs of interference from exotic fields. Their models revealed hints of quantum coherence in regions where classical physics predicted chaos. Narrow spikes within the waveform suggested brief interactions with negative energy regions, exotic phenomena required for theoretical constructs, like traversable wormholes. While negative energy has never been observed in macroscopic form, quantum systems allow it to arise transiently. Like flickers in the vacuum, the signal's fluctuations behaved as though it had passed through a region where quantum fields were manipulated in ways nature rarely permits. Such regions, if they existed, might act as corridors where space-time geometry becomes malleable. A wave entering such a corridor might re-emerge, shifted in time, as though space and time had intertwined. The possibility was extraordinary. Yet, the data leaned toward it with silent insistence. Other theories emerged as scientists probed the signal's dispersion. Waves traveling through space-time accumulate delays based on the density and charge of the medium they cross. The anomaly's dispersion curve, however, carried a signature not found in the interstellar medium. Its behavior resembled a wave passing through an area with altered spacetime metrics, the kind predicted in simulations involving massive rotating objects or engineered spacetime structures. The conclusion remained speculative, but increasingly difficult to avoid. The signal had interacted with something capable of bending time. Yet the greatest shock did not come from the cosmic journey, nor from the spectral distortions. It came from a deeper layer hidden within the overall structure of the anomaly. As analysts reconstructed the waveform in full, a truth emerged that carried more weight than any gravitational explanation. The signal was human, Its structure matched an outgoing template not yet transmitted. The calibration pattern, designed by the observatory's software, bore features that no natural phenomenon could replicate. The shape of the modulation, the timing of the pulses, the compression structure, all were artifacts of human engineering. And yet the signal had arrived before its source. The more scientists probed the anomaly, the more it resembled a reflection of something familiar. Not an alien transmission, not an astrophysical event, but a message from an iteration of humanity that had not yet acted, or perhaps from a branch of time where events had unfolded differently. The possibility raised haunting implications. If the signal was truly a return of humanity's own broadcast, then the universe had momentarily allowed a loop to form, a path where information circled back across the timeline, like a ripple returning to its origin. Such loops were not forbidden by general relativity, but were believed to be prevented by cosmic censorship or quantum instability. Yet here was evidence that time, under certain extreme conditions, might become porous. The deeper investigations revealed a series of correlations between the anomaly and the calibration template that bordered on the uncanny. The signal matched not only the outgoing pattern, but also predicted minor changes the team intended to implement, updates not yet made, instructions not yet written. It behaved as though it carried knowledge of events that had not yet unfolded. This temporal mirroring intensified the mystery. If the universe permitted even brief windows where information traveled backward, then the past and future were not strictly separated. They were woven together in ways that defied classical understanding. A message from the future implied a future sender. Yet no such sender existed. The calibration pulse was routine. It carried no encoded message. It had no purpose beyond internal systems. How could it return transformed, touched by something beyond the present? As the investigation deepened, global scientific community confronted an unnerving realization. The anomaly carried no signature of external intelligence. No variation in structure suggested modification by an outside source. No additional information hinted at communication. It was not a message. It was a mirror, a reflection of human technology bouncing off a boundary in time. Perhaps the most disquieting conclusion came from theoretical physicists who studied models of time-symmetric quantum mechanics. In their view, events in the universe might not be strictly bound to a forward direction. Instead, the universe might operate according to boundary conditions set both in the past and the future, a system where time was not a flowing river, but a static landscape through which information could travel under rare conditions. In such models, the anomaly made sense. It was an expression of a deeper symmetry, a glimpse into the full structure of time. Yet this interpretation raised unsettling questions. If events were shaped by both past and future conditions, then the future was not merely unknown, it was active. It participated in the unfolding of the present. The universe in this light behaved not like a machine marching forward, but like a tapestry woven from threads extending in both directions. Scientists stood before this possibility with a mixture of awe and dread. The anomaly had opened a doorway into an aspect of reality they were unprepared to confront. The question was no longer how the signal arrived early. The question was why the universe had allowed it to be seen. As data poured into global networks, the pattern grew clearer. The anomaly was not a cosmic message. It was not an extraterrestrial transmission. It was something more intimate and far more troubling. A return signal from a future that depended on the present. The investigation, now deeper than any before it, pointed toward a single, astonishing possibility. Humanity had glimpsed a fragment of its own timeline, a path the universe allowed only briefly before closing again. In the quiet aftermath of this realization, one truth lingered like a faint echo in the collective mind of the scientific world. The signal had not come from the stars. It had come from the future, and the universe had allowed the present to see itself just once, reflected across the surface of time. The days that followed the initial investigation unfolded with a quiet, growing tension, the kind that precedes a storm whose shape cannot yet be seen. Scientists around the world continued to monitor the sky, searching for a repetition of the anomaly. Some hoped it had been a singular event, a fleeting disturbance in the cosmic fabric. Others felt a different expectation, as though the universe had opened a door and was not finished speaking through it. In the silence between detections, anticipation filled the observatories like a second atmosphere. The return came without warning. In the early hours of a cold morning, when the sky above Chime was still scattered with the pale remnants of starlight, another pulse entered the array. It slipped into the system with the same quiet precision as the first, bearing the same delicate structure, the same soft modulation, the same uncanny coherence. But this signal carried something new, something far stranger than the earlier anomaly. Embedded within the waveform was a sequence of metadata referencing technical specifications that did not yet exist. The calibration template it matched had not been written. The software update it reflected had not been coded. The harmonic structure it displayed aligned with parameters that the engineering team had discussed only privately. In draft proposals and incomplete design notes, these updates were weeks away from testing, months away from deployment, yet the signal bore them with perfect accuracy. As though the future had already installed them, the implications settled on the team with a weight far heavier than before. The anomaly was no longer a single moment where time had folded. It was evolving. It was interacting. It was expanding its temporal reach. As scientists analyzed the new signal, they realized that the timestamp gap had widened. The first anomaly had arrived only hours early. The second had arrived days early. If the phenomenon continued, future detections might precede their own origin by weeks, months, or more. Time, once a stable axis, was now behaving like a stretched membrane, elastic, trembling, capable of bending into shapes no human theory had ever predicted. Across international research centers, the realization settled with a slow unease. The anomaly was not a burst from the cosmos. It was a timeline feedback, a loop forming somewhere in the structure of reality. Gradually widening its mouth, the scientific world entered a theoretical crisis. In the quiet halls of universities, in late-night discussions between physicists, in encrypted online meetings between experts, one question emerged again and again. What mechanism could possibly create such behavior? Some theorists proposed that the anomaly might be the result of a naturally occurring space-time loop, a region where gravitational curvature became so extreme that time folded back on itself. In their view, the signal might have grazed a rotating black hole, falling briefly into the mathematically predicted domain of closed timelike curves before re-emerging along its path. Such loops existed in equations, but were believed to be unstable, collapsing under the slightest quantum disturbance. To see one in action required a convergence of conditions, so rare that the universe might produce them only once in billions of years. Others rejected the black hole explanation. The signal's fidelity remained too pristine, its coherence too stable, its structure too human to have passed through such a violent environment. Instead, they proposed something even stranger, the idea that the universe had briefly torn open a shortcut through temporal geometry. An event similar in nature to a wormhole, but oriented across time rather than space. In this interpretation, the anomaly reflected not a cosmic journey through extreme gravitational curvature, but a moment where 2 points on the same timeline briefly touched. Allowing information to flow freely, though radical, the idea found quiet support. Space-time, defined by Einstein's equations, possessed a geometry more flexible than intuitive experience suggested. It could curve, twist, stretch, and ripple. If it could form shortcuts across distance, then under rare conditions, it might also form shortcuts across time. The universe might occasionally create bridges not between places, but between moments. Such possibilities forced physicists to confront a new kind of fear. If space-time was capable of self-interaction across temporal boundaries, then time itself might not be a fixed sequence of events. It could behave like a resonant surface, echoing under the pressure of extreme conditions. A signal sent into such a region might scatter not forward, but backward. Rebounding into earlier epochs, the existential implications were profound. If information could cross the boundary of time, then the universe might not be a timeline at all, but a dialogue. Events in the future could influence events in the present and in turn be shaped by them. Reality could exist not as a chain of causes and effects, but as an intricate feedback loop where past and future co-created one another in ways invisible to ordinary experience. As the scientific community confronted this possibility, a new question emerged quietly, uncomfortably, in the minds of many. If the universe allowed such a loop to form, was it accidental or intentional? Not intentional in the sense of consciousness, but in the sense of structure. If space-time possessed deeper symmetries than currently understood, it might allow information to propagate along paths unknown to classical physics. Quantum mechanics already suggested that the universe did not strictly separate past from future. In some interpretations, the universe behaved like a block of space-time, a four-dimensional structure where all events coexisted, and where boundaries between time slices were merely perceptual. In such a universe, the flow of time might be an illusion created by the way consciousness experiences change. The anomaly, in this view, was not an aberration, but a revelation, a brief, accidental glimpse into a deeper reality where time's arrow was not fundamental. Yet, the anomaly refused to settle comfortably into any theory. The new signals reference to uncreated data strained even speculative models. Barely a week earlier, the updated calibration template had existed only in the minds of engineers and in drafts on isolated computers. For the signal to carry this information, the future in which the update existed had to be real enough to transmit its signature. Even though that future had not yet occurred in the present timeline, this suggested a branching structure in time, where multiple versions of events coexisted. In one branch, the calibration update had been completed, tested, and transmitted. In another, the update was still a concept. The anomaly behaved as though these branches had intersected or overlapped before diverging. Again, such models found resonance with interpretations of quantum mechanics proposing that the universe did not choose a single outcome, but evolved through a vast superposition of possible futures. If so, the anomaly might represent a moment where the wave function of reality briefly aligned multiple timelines, allowing information from one branch to leak into another. The possibility introduced an unsettling question. What if the anomaly was not a rare occurrence, but a fundamental property of the universe that only manifested under specific conditions? What if the timeline was always in dialogue with itself, but humans lacked the sensitivity to perceive the conversation? As the new signal continued to be analyzed, more anomalies surfaced. The phase structure of the waveform contained fluctuations that resembled faint interference. Patterns oscillations created when two nearly identical signals overlapped in time. These patterns were not present in the first detection. They suggested that the two versions of the calibration template, the current and the future, were interacting, their differences producing a kind of temporal interference. The pattern hinted at a deeper truth. The anomaly was no longer a single event. It had become a system, a cycle, a feedback loop between now and the not dashed yet in meetings across continents. Physicists debated whether they were observing the birth of a temporal resonance, a self-reinforcing interaction between different points in time. If this resonance grew stronger, the gap might widen, and signals could arrive weeks or even months before their origin. Such a progression would not merely challenge human understanding of time, it would reshape it. Amid this theoretical upheaval, one realization carried more weight than all others. The anomaly had escalated beyond the boundaries of physics. It now brushed against the foundations of existence. It forced humanity to confront the possibility that reality was never intended to be linear. The more scientists studied the signal, the more its nature slipped beyond the language of ordinary science. It behaved like a reflection, but also like a prediction. It carried human information, yet it arrived from a place beyond human reach. Its coherence suggested intention, while its distortions suggested natural forces. It existed at the boundary between the familiar and the impossible, refusing to align with any singular category. The widening timestamp gap created a haunting implication. The future might not be a destination, but an active component of the present. In the anomaly's structure, the present did not merely move toward the future moved toward the present. This realization settled like a quiet revelation across observatories, universities, and research labs. The anomaly did not simply suggest a bending of time. It suggested a conversation unfolding across the fabric of reality. The universe was not a machine running forward. It was a dialogue between moments, a self-observing system exploring its own possibilities. The signals once seen as data artifacts now resembled whispers in a vast temporal architecture, hints of a deeper communication between different layers of existence. If this was true, then every moment might contain hidden traces of both past and future, intertwined in ways too subtle for ordinary perception. The second anomaly marked not the continuation of a mystery, but its expansion. The cosmos had opened a window into its temporal structure, offering a glimpse of a universe that did not obey the familiar rhythm of time. Instead, it pulsed with a complexity far greater, a richness of interaction where past and future shaped one another. As the world of physics grappled with these revelations, the quiet dread of a deeper truth emerged. The anomaly might not be limited to signals. If the fabric of time could fold for radio waves, it could fold for anything. A future event might imprint itself on the present. A future discovery might ripple backward. The boundaries between what had happened and what would happen might be far more porous than anyone imagined. The universe, in this view, was not a timeline at all. It was a living geometry, one capable of turning back to look at itself. And humanity, for the first time, had caught that gaze as the anomaly deepened. The scientific world entered a different phase of inquiry, one that required stepping away from the comfort of established knowledge and into the vast, trembling space of speculation. The earlier investigations had clarified one truth: the signal was real. It was coherent. It carried human information, and it arrived before its own origin. Everything that followed had to contend with this contradiction. The universe had behaved in a way that defied classical expectations, and so scientists turned toward the outer edges of theoretical physics, where the strange becomes possible and the impossible becomes a question rather than a barrier. The first and perhaps most anticipated explanation emerged from general relativity itself. From the geometry that Einstein envisioned more than a century earlier, among its many astonishing predictions lay a peculiar concept known as the closed, timelike curve, a path through space-time that loops back on itself. In ordinary experience, time flows forward, its arrow pointing toward the future with unwavering consistency. But in the curved space-time surrounding rapidly rotating black holes, relativity permits the existence of regions where this arrow bends and twists, forming loops. A particle or signal traveling along such a path could, under the right conditions, return to an earlier point in its own history. Physicists studying the anomaly wondered whether the signal had grazed such a region. A rotating black hole, a Kerr black hole, dragged space-time around it in a powerful whirlpool. Inside this rotating frame, mathematics allows trajectories that move not only through space, but backward through time. If the signal had wandered briefly into the distorted geometry near such an object, it might emerge earlier than expected, carrying its own information from the future. Yet the idea carried complications that resisted easy acceptance. The turbulence near a rotating black hole is severe. Any signal passing near the ergosphere would undergo dramatic distortion, its structure scattered by intense gravity. But the anomaly remained pristine, almost impossibly clean. The slight gravitational fingerprints it carried hinted at curvature, but not at the chaos expected from such proximity. The coherence of the signal argued against a journey through a black hole's domain. The mathematics permitted it. The physics resisted it. The explanation, though alluring, failed to fully embrace the anomaly's elegance. As this idea faltered, attention turned toward quantum mechanics, a realm where the rules of time often appear less rigid than in classical physics. Among the strangest concepts in quantum theory lies retrocausality. The possibility that under certain conditions, information may appear to travel backward. Experiments such as the delayed choice quantum eraser have shown that the behavior of particles can be influenced by measurements made after those particles have already been detected. These results do not transmit usable information to the past, but they challenge intuitive notions of time's flow, revealing a world where outcomes depend on future choices. Scientists studying the anomaly considered whether the signal represented a macroscopic manifestation of such quantum behavior. Perhaps entanglement had played a role. Perhaps the calibration pulse, prepared in the future, became entangled with vacuum fluctuations, allowing its structure to echo backward in time before emission. In laboratory experiments, quantum states can correlate across vast distances, ignoring classical limits. Could a similar mechanism allow information to correlate across time? Yet the limitations of quantum retrocausality were well known. While quantum experiments sometimes blurred the distinction between past and future, they have never permitted controllable information to be sent backward. They influence probabilities, not signals. They change statistical outcomes, not the transmission of structured data. The anomaly was too coherent, too intentional, too unambiguously macroscopic to be explained by quantum subtleties alone. Retrocausality hinted at the behavior observed, but did not fully embrace it. The signal remained a structured broadcast, not a probabilistic ripple. Quantum mechanics alone could not bridge the gap. The next theory pushed speculation deeper into exotic territory, the possibility of wormholes. Wormholes, if they exist, represent tunnels through space-time, linking distant points in ways that surpass the speed of light limit. Under specific mathematical conditions, wormholes may even link different moments in time. If one end of a wormhole experienced time dilation relative to the other, by being placed near a black hole, or accelerated to near light speed, its temporal alignment would shift. A signal entering one mouth could emerge from the other at an earlier moment. Such constructs require negative energy or exotic matter to stabilize, something quantum theory permits in microscopic amounts. Physicists wondered whether the anomaly might have traveled through such a tunnel. The slight exotic signatures embedded in the signal suggested interference from fields not typically observed in nature. Negative energy appeared in the form of tiny fluctuations. It's the kind predicted by quantum field theory, but never experimentally harnessed. These delicate markers sparked speculation that the signal had briefly crossed a region of spacetime where exotic matter played a role, a region where a microscopic wormhole might have opened for a fleeting moment before collapsing. Yet this theory also strained under scrutiny. While wormholes appear in Einstein's equations, no evidence suggests they occur naturally, let alone in forms stable enough for coherent signals to traverse. Their existence requires extreme conditions that may not arise in the universe without deliberate engineering. And even if a microscopic wormhole did appear, it would likely collapse far too quickly to preserve the clarity of the anomaly. The mathematics allowed the concept. Nature offered no examples. The signal was too refined to have passed through something so unstable. With classical relativity and exotic geometry failing to offer complete answers, scientists explored a different possibility, the topology of the universe itself. In certain cosmological models, the universe contains folds, subtle warps, created during rapid inflation. Moments after the Big Bang, these folds may bring distant regions of spacetime into close proximity. If the universe contains such folds in its temporal dimension, then certain trajectories might allow information to bypass linear progression, slipping from one time layer to another. Physicists studying cosmic topology proposed that the anomaly might have followed such a path. The distortions in the signal resembled patterns. If the wave had crossed a region where the metric of space-time shifted in non-intuitive ways, if a fold had aligned to temporal surfaces, even for a moment, the signal might have traveled along the fold, emerging earlier than expected. Such an occurrence would not require the violent forces of black holes or wormholes, only an alignment of cosmic geometry. Yet the refined structure of the anomaly pushed against this explanation as well. A cosmological fold might allow temporal shortcuts, but it would not reproduce human-created data with such precision. It would not anticipate future updates and calibration templates. The topology model explained the timing, but not the intimate detail. As theories strained under the weight of contradiction, some researchers turned to the multiverse, a conceptual landscape in which countless versions of reality coexist, following different paths. In a multiverse connected by quantum branching, information might occasionally leak between parallel timelines. A signal sent in one branch could appear in another. If a future version of Earth transmitted a calibration pulse, it might in principle cross into an adjacent timeline where that pulse had not yet been written. The anomaly in this model was an echo from a neighboring future. This idea carried an eerie elegance, offering an explanation for the signal's knowledge of uncreated data. In another timeline, the update may already have existed, encoded, transmitted, detected. The anomaly would then represent a moment of cross-branch interference, a brief resonance between two versions of reality. The multiverse might allow such interactions under rare conditions, though the mechanism remained unknown. Yet this theory too faltered at its edges. Multiverse models predict enormous divergence between parallel timelines. A calibration pulse, simple and routine, might appear similar across universes, but the perfect match of metadata, formatting, and compression was improbable. The signal had not merely resembled human output. It had copied it exactly. Quantum branching could not easily explain identical data appearing across separate realities. One by one, the theories rose into possibility only to fall away under scrutiny. Closed timelike curves explained the time loop, but not the clarity. Quantum retrocausality explained the temporal inversion, but not the macroscopic coherence. Wormholes explained the shortcut, but not the stability. Cosmic topology explained the timing, but not the prediction of future data. Multiverse leakage explained the prediction, but not the precision. And yet, remarkably, none of the theories contradicted the anomaly entirely. Each captured a fragment of the truth. Each illuminated a different facet of the mystery. So the anomaly existed at the intersection of several domains: quantum, gravitational, cosmological, and topological. It behaved like a composite phenomenon, a convergence of extreme conditions that allowed information to slip beyond its ordinary constraints. Every attempt to explain the anomaly faced the same obstacle: fidelity. No known structure, natural or theoretical, could carry a structured, human-generated signal backward in time with such precision. No known physical system could preserve its coherence across such a journey. No quantum mechanism could encode future templates into a present transmission. The anomaly defied each theory individually, yet existed comfortably within the overlapping region, where all theories hinted at something deeper. A hidden property of space-time not yet uncovered. Mathematically, the signal was consistent. It obeyed the equations. It fit into the structure of relativity and quantum mechanics when viewed from unconventional angles. It existed within the boundaries of possibility, but at the very edge, pushing against the limits like a hand pressed gently against a thin barrier. And perhaps that was the clearest indication of its nature. The anomaly remained an impossible event, perfectly executed, a contradiction, yet mathematically sound. An error in the universe's behavior, yet patterned and deliberate. A message not from elsewhere, but from elsewhere. A structure that defied explanation, yet refused to break the language of physics. Theories rose and fell, but one truth lingered at the margin of every conversation. The anomaly had not broken the laws of physics. It had revealed the parts of those laws humanity did not yet understand. In the quiet hours of late-night calculations, in the glow of observatory screens, in the silence between theoretical arguments, a subtle realization emerged across minds separated by continents but united in purpose. The signal was a perfect anomaly, not supernatural, not magical, not alien, but a reflection of a reality more complex than anyone had imagined, a universe where time can fold, layers can touch, and the future can whisper into the present. In the weeks following the second anomaly, the world of science entered a new phase, no longer a state of shock, but a kind of mobilization. It was as though humanity, long accustomed to observing the universe from the safety of the present, had suddenly been invited to participate in an experiment orchestrated by the cosmos itself. The signal from the future had shaken the foundations of physics. And now, a global effort began, quiet but enormous, to determine whether this violation of time was a fleeting accident or the first window into a deeper reality. Across continents, telescopes shifted their gaze. Laboratories reorganized their priorities. Agencies recalibrated their missions. The anomaly had opened a door, however briefly, and humanity rose to meet it with instruments crafted from centuries of knowledge. With a growing sense that the universe was far stranger than its surface suggested. The first step was synchronization. Scientists began constructing networks of ground-based and space-based receivers designed to operate in perfect temporal harmony. Timing errors of even a few nanoseconds were unacceptable. The phenomenon they sought to capture lay not in the amplitude of signals, nor in their frequency, but in the faint distortion of time itself. Ultra-stable atomic clocks, the most precise machines ever built, became the backbone of this global network. Optical lattice clocks, capable of measuring time so accurately they would not lose a second in billions of years, were linked. Across continents and synchronized with satellites orbiting high above Earth, these clocks were not merely instruments. They were anchors in the shifting sea of space-time. Reference points against which the universe's strange behavior could be measured. In observatories from Hawaii to Chile, engineers installed new timing receivers connected directly to these optical clocks. Each receiver listened not only for cosmic signals, but for the smallest ripple in temporal alignment. The goal was simple, yet profoundly ambitious: to detect another moment where the future touched the present. Meanwhile, space agencies repurposed existing assets for the investigation. The Deep Space Network, humanity's long-range communication lifeline to faraway probes, became a silent participant in the search. Its antennas, spread across California, Spain, and Australia, monitored signals returning from Voyager, New Horizons, and other distant craft. The network's time delay records, normally used to track spacecraft, were now studied for discrepancies, looking for tiny deviations that might hint at temporal distortions. If space-time warped near Earth even subtly, these deep space signals might carry hints of its bending. Gravitational wave observatories joined the effort as well. LIGO, Virgo, and KAGRA instruments, built to detect the faint ripples of colliding black holes, now listened for quieter tremors. Ones not caused by cosmic cataclysms, but by the delicate shifting of space-time geometry. The anomaly suggested that time itself might be flexing, however briefly. A wormhole-like event, a temporal fold, or the formation of a closed timelike curve could produce a signature too soft for traditional gravitational wave detection. Perhaps resonant enough to appear as faint, anomalous noise. Teams combed through archived data for any such hints. Optical interferometers, devices sensitive enough to detect distortions smaller than a proton, were deployed and enhanced. Scientists used them to measure tiny shifts in spacetime, hoping to catch the signature of a temporal distortion at Earth's surface. Even microscopic warping could reveal the presence of exotic structures. Such distortions might appear as phase shifts in laser beams traveling along perfectly aligned paths. If time folded, even for an instant, the interference patterns would betray its presence. These instruments formed the sensory network of a species attempting, for the first time, to listen for echoes across time rather than space. The world's largest observatories contributed their strengths. The James Webb Space Telescope, orbiting far from Earth's glow, added deep-field timing scans to its schedule. Its exquisite sensitivity allowed it to detect faint cosmic signals with unprecedented clarity. Though JWST was built to look outward into the ancient past, its detectors now searched for irregularities in the timing of distant light, subtle clues that might reveal distortions in space-time structure. ESA's Euclid mission, designed to map the geometry of the dark universe, became another essential participant. Its observations of dark matter topology offered insight into how cosmic structures might affect temporal behavior. If the anomaly arose from a region of warped spacetime, Euclid could pinpoint its shape, revealing whether dark matter, filaments, or voids played a role in altering the temporal metric. Other missions were planned or modified to explore the phenomenon. Future satellites designed to measure black hole spin, event horizon turbulence, and high-energy cosmic rays were assigned secondary objectives to search for signs of spacetime. Anomalies matching the timing signatures observed on Earth. The universe, after all, might not restrict such phenomena to a single location. Humanity had begun building the tools to question time itself as this global infrastructure developed. Scientists continued to probe the anomaly with new analytical techniques. They explored whether a future signal might correlate with gravitational wave events, or whether a ripple in spacetime might precede its own detection. Some theorists suggested that the anomaly might generate a subtle shadow in spacetime, before its arrival, detectable as a distortion in local geometry. Others believed quantum sensors might capture changes in vacuum fluctuations, a slight trembling in the quantum fields surrounding Earth. Quantum phase detectors were designed to observe these fluctuations. Normally, the quantum vacuum seethes, with activity virtual particles appearing and vanishing, fields oscillating in silence. But a distortion in time could alter these fluctuations, producing patterns that hinted at temporal reflection. If the anomaly interacted with quantum fields, the detectors might register a faint, unexplained signature, noise that was too structured to be noise, too soft to be a classical signal, too coherent to be dismissed. Amid this technological mobilization, the scientific community focused on three primary targets: another backward-timed signal, a space-time ripple indicating a temporal shortcut, and a quantum phase shift suggesting a time-reflective event. The first target was the most direct. If the anomaly repeated, the global network might detect it from multiple locations, allowing triangulation of its path and analysis of its distortions. The second target, a ripple in spacetime, would support theories involving wormholes, gravitational loops, or temporal folds. The third target, quantum phase shifts, would provide insight into whether the anomaly interacted with the universe at its most fundamental level. Every tool had a role, each one illuminating a different aspect of reality's hidden structure. In the months that followed, the network grew more sensitive. Time measurement precision improved by orders of magnitude. Interferometers were calibrated to detect distortions smaller than ever before. The Deep Space Network refined its timing algorithms. JWST captured new data. Euclid mapped cosmic structures with greater clarity. The gravitational wave observatories updated their filters to identify unusual signatures. It was during this period of heightened sensitivity that something extraordinary occurred. For the briefest moment, optical clocks across several observatories registered a synchronized anomaly, a deviation so small it lay deep within the margins of uncertainty. Yet its pattern was unmistakable. It did not resemble a drift, nor a failure, nor a mechanical error. It resembled the signature projected in simulations of temporal turbulence, a tiny, localized shift in the rate at which time flowed. The anomaly lasted less than 1,000th of a second. It vanished before it could be confirmed. But its structure matched the theoretical profile of a space-time ripple, the sort that might accompany the opening or closing of a microscopic wormhole or the formation of a small temporal loop. This ripple, though unverified, stirred the scientific world with a quiet electricity. It suggested that the anomaly was not an isolated broadcast, but part of a larger phenomenon, a fluctuating structure within space-time that might open and close unpredictably. A temporal wave, perhaps, resonance. The possibility ignited new forms of collaboration. Simulations explored how temporal distortions might propagate through the universe. Models examined how black hole spin might influence time loops. Studies explored whether dark energy, with its mysterious push on the cosmos, could alter temporal geometry. Theories multiplied, each one testing the boundaries of what physics could allow. Yet even as the tools grew more sophisticated, the anomaly itself remained elusive. No new signal arrived, no new ripple formed, no quantum phase shift emerged with certainty. It was as though the universe had spoken twice. Once in a whisper, once in an echo, and then fallen silent again. But the silence did not diminish the resolve of those who listened. Humanity's instruments now stretched across Earth and into space, forming a lattice of sensors capable of detecting changes in space-time finer than ever before. For the first time, the species was prepared not merely to observe the universe, but to listen for its deeper hidden rhythms, the ones that might transcend the boundaries of time. In this newly awakened age of observation, philosophical understanding began to emerge. The anomaly was not merely a scientific event. It was a prompt, a subtle invitation to reconsider the nature of reality. Time, long regarded as a linear progression, had revealed its fragility. The universe, once thought to be a silent backdrop on which events unfolded, seemed now to possess its own internal dialogue, the scientific tools built to detect. The anomaly's return did more than measure signals. They represented humanity's attempt to enter that dialogue, to understand the language in which the universe spoke to itself. And though the anomaly remained hidden, the tools stood ready, waiting for the next whisper from the future, the next bend in time, the next tremor in the cosmic fabric. For the first time, humanity had prepared itself not just to explore the universe, but to question time itself. In the quiet months that followed the surge of scientific activity, the universe offered no further answers. No new signals arrived. No fresh anomalies shook the structure of time. The instruments remained poised in their silent vigilance, waiting for another whisper from the unknown. Yet the silence itself carried a weight, as though the cosmos had spoken just enough to alter humanity's understanding, and then withdrawn into its deep and ancient stillness, as the global network of observatories settled into their new rhythms. A different kind of inquiry began to unfold, not in laboratories or on whiteboards, but in the quiet minds of those who had witnessed the anomaly. It emerged in the pauses between calculations, in the lingering moments at observatory windows, in the nights when the sky stretched overhead like an endless, unbroken question. The anomaly remained a point of mystery, a moment where the future reached into the present. But beneath the scientific theories and technical explanations, a deeper reflection took form. If the universe could speak across its own timeline, what was it trying to say? The question hung like a distant star, faint yet inescapable. Throughout history, humanity had searched for meaning in the heavens, in constellations, comets, in the patterns of planets, in the faint glow of ancient starlight. But this anomaly was different. It did not merely appear from the depths of space. It emerged from the depths of time. It carried human structure, human information, human fingerprints. It arrived from a moment not yet lived. It was as though the universe had offered a glimpse not of distant galaxies, but of the world ahead, and so the reflection deepened. What if the anomaly was not a message in the conventional sense, but a reminder of a truth overlooked? What if time was not a river flowing in one direction, but a mirror, a surface that could bend, reflect, ripple? What if past and future were not divided by an insurmountable boundary, but intertwined, each shaping the other in ways too subtle for ordinary perception? Physicists had long debated whether time was fundamental or emergent, whether the arrow of time arose from entropy or consciousness or cosmology. But the anomaly hinted at something more profound, that time itself might be part of a larger story the universe was telling. A story not constrained by linear progression. In this story, the future might not be a distant horizon, slowly approached by the present. It might be an active participant in the unfolding of reality, influencing the present, shaping it from beyond the visible boundary of now. This idea carried both awe and unease. If the future could reach backward, then the present was not isolated. It was connected to something larger, something that spanned across time like an unbroken fabric. Every moment, no matter how fleeting, might be part of a wider design not predetermined, but intertwined with possibilities yet to occur. The anomaly had shown that the future was not silent. But what did it mean for humanity to receive such an echo? Was it an accident? A cosmic coincidence born from gravitational turbulence or quantum resonance? Or was it an inevitable expression of a universe where time is flexible, where events resonate across centuries and millennia, the way vibrations travel across the surface of a drum? In the contemplative quiet of these reflections, one idea emerged with gentle strength. Perhaps the anomaly had not been an intrusion of the future into the present, but a reminder that the present itself participates in the shaping of time. Perhaps humanity had never been a passive observer drifting forward through a linear sequence of moments. Perhaps, without realizing it, every action, every discovery, every question sent waves not only into the past and future, but across the deeper structure of space. If this were true, then the anomaly was not a disruption, it was a revelation, a tiny opening in the fabric of reality, revealing the interconnectedness of all moments. Some scientists found themselves turning to an idea older than modern physics, older even than philosophy, the notion that the universe is not a cold machine, but a kind of unfolding story. Stars are born, live, and die. Galaxies collide and merge. Particles interact and dance. Life emerges from the dust of ancient suns. All these processes carry a narrative quality, not driven by intention, but by the elegance of physical laws, by the evolution of complexity, by the tapestry of cause and effect. The anomaly added a new layer to this cosmic story. The possibility that the story is not written from beginning to end, but from all directions at once, that the universe tells itself across time, weaving threads from future to past as easily as from past to present. This idea invited another reflection. What does it mean for humanity to exist within such a story? If reality is a dialogue, then humanity is not merely a reader of the universe, it is a participant. Every discovery contributes to the unfolding narrative. Every insight shapes the world. Every question extends the boundary of understanding. The anomaly suggested that this participation might run deeper still, that humanity's actions might resonate not only forward but backward, influencing the trajectory of events in ways unseen. It raised the possibility that consciousness itself might be part of the equation. Physics had never fully resolved the role of observation in the behavior of quantum systems. The very act of witnessing altered outcomes. If time itself could bend, then consciousness might not merely observe reality, it might be woven into its structure, shaping the possibilities that define both past and future. And yet, for all these reflections, one truth remains steady. The anomaly had not revealed why the universe behaved this way. It had not answered the deepest question, whether time's flexibility served a purpose, or whether it was simply a natural consequence of the universe's geometry. It had not explained why the signal returned, nor from what future it came. It had presented a mystery without granting resolution. This unresolved truth became the emotional heart of the investigation. Lingering in the minds of those who studied it, there was beauty in the uncertainty, a reminder that the universe still held depths beyond imagination. There was humility in the realization that humanity, for all its progress, had touched only the surface of reality. There was wonder in knowing that even after centuries of exploration, the cosmos remained capable of astonishment. As the anomaly faded into memory, it left behind a quiet transformation. Scientists continued their work with new instruments and deeper questions. Observatories scanned the sky with renewed purpose. Theories evolved. Models grew more complex. But beyond the equations and measurements, something had changed in the way humanity looked at time. The anomaly had revealed that time is not merely a path. It is a landscape. A terrain shaped by gravity, by energy, by quantum fields, by the curvature of the universe itself. A terrain that may contain valleys and ridges, folds and bridges, loops and echoes. A terrain where the future is not a destination, but a dimension woven into the fabric of existence. In this terrain, the anomaly was a landmark, a point of illumination, showing that the universe is more connected, more dynamic, and more mysterious than previously imagined. And so the chapter closes with a quiet, contemplative understanding. The anomaly may never return. Its origin may remain forever unknown. Its implications may take generations to unravel. But it has already shifted the boundary of what humanity can ask, what humanity can imagine, what humanity can become. For the signal carried no message beyond its own existence. Yet its existence was message enough, a brief moment in time where the universe reached back toward the present, a whisper from a future that remembered an event not yet lived, an echo that revealed the delicate, intertwined structure of reality, a reminder that the cosmos is not silent, only subtle, not distant, only immense, not fixed, only unfolding in the end. The realization settled like stardust across the minds of those who listened. Humanity had sent no message, yet the universe returned one, a whisper from a future that already remembers them. And in that whisper lay the promise that the story of time, complex, layered, and beautiful, is only just beginning. The end. If questions like these spark your curiosity, then make sure to subscribe to Late Science Universe and hit the bell icon so you never miss our next journey into the greatest mysteries of the cosmos. See you in the next video. Thank you. Poetic lines. Beyond the stars lie worlds unseen, and Late Science Universe still has many dreams to explore.